Okay, one more stream before I fall asleep. I'm super tired. I don't know how. But we have one more chapter to read. That's what I aim to do today. And then tomorrow we're going to do Unsafe Rush, which is super fun. I like living in danger. I guess no. Okay, so before that we do some safe stuff first, and then we have a final project. I don't know if I have time to do Wow, I'll be super busy tomorrow if I do final project. I'll see. Maybe I'll do it after Berlin when I come back from Berlin. But then after that we only have final project and rustling exercise left after 18 and 19. So we'll see. Ideally, want to do the final project and then leave rustling to maybe I want to finish before the end of July. So we'll come back from Berlin and then do the rustling. But if not, then we'll see what's going on. Maybe I can stream from Berlin. We will see. So pattern and matchings. Patterns are a special syntax. Yes, we all loved it, right? Rules for matching against structure of types, both complex and simple. So you can match literals, the structured stuff like arrays, enum, structs, or triples, variables, wildcards, placeholders. So what are they? So for example, like this, sum. Use a pattern, we compare it to some value. Pattern matches the value, then the value. Use the value part in our code. So for example, match expression, we do that a lot. This chapter is a reference on all things related to patterns. We will cover the valid places to use patterns, the difference between referable and irreferable patterns, and the different kind of pattern syntax that you may see. Okay. So let's just jump into it. All the patterns we can use. Pattern expression. So match value pattern expression. This is like the match arm, so we have seen it multiple times. Sum, and it would have a sum I plus 1 that got returned. So we can also have underscore, which is like matching everything else, which is super handy. We match everything, never bind to a variable. Using the last match arm, basically just very lazy, right? Because if you don't do that, then the compiler is not happy. Then you can just use underscore to take care of the rest. Be useful when you want to ignore any values not specified. Ignoring values in a pattern session later. Conditional if let. So again, like we have just seen if let earlier today. It's everywhere. Maybe it's a short way to write a equivalent of match. Only matches one case. So if let can have a corresponding else if let doesn't match. So possible to mix and match. Mix and match. If let, else if, and else if let. So what do we do here? So favorite color option, that is a string, that's none for now. It's Tuesday, is false, age is result, is a U8. So it's 34 dot parse. So let some color. So if let some color equals to favorite color. So if let, so this will become the favorite color, right? So if favorite color is some color, if it matches, so you have something that will print as favorite color. If none, it's a favorite color as the background. If none, then it will go to the else. So F is Tuesday, so you have more condition. Then Tuesday is the green day. So L if let, okay, age. So if age is also, so there's an age, right? There's okay. Then we have the age. Age is greater than 30. The proposed background, else, if nothing matched, then use this blue. Yeah. So this one, I think, because it's not Tuesday, so it won't be green. It doesn't have the color, so it will be using the age is greater than 30 because 34. So purple, I think. Yeah, so this will good give us the purple. Yeah, if it's passed correctly. If it's something else, then it won't. Then it will just use blue. So yeah, this is unnecessarily complex, but it's just showing that you can mix all of them to use. So basically, if using mixing if let, else if, and else if let, or an else and everything is overly complicated for the for sake of demonstration. Here's shadow variable in some way that matches can. So this age will become an age here. Yeah, so color would be the color here, which is the favorite color, but it's not some color, so it's not here. Yeah, we have the age that we could matches. Using if less is that compiler doesn't check for exhaustiveness. Because everything goes to else or abyss. So if let doesn't check for exhaustiveness, but match does, or meet the last L blocks, then nothing will happen. If someone doesn't have a possible age, if someone put like apple here, then it won't have, then nothing happen. Okay, while let conditional loop. While let some, so it's the same kind of thing. The stack will pop out something or none. So if it's something, then we'll extract the top and then use the top here. So while let, similar kind of thing. So we have push 1 2 3, so it will become 1 2 3 here. No, it's a stack, so it push 3 to 1. Yeah, 3 to 1, and then it is and it will pops none, so it's none. Then it will stop. Yeah, it will stop because it doesn't match the sum here. For loops. For loop, we can also do that. So the thing that come out, so v iter will give out 1 2 3, the 3 of these, and then you eliminate. So 1a 2b, no, 0a 1b 3c, I think. So it will be index and value here. Yeah, and then let statement. Only explicit discuss match and if let. Oh, actually let is also a match statement, matching statement, not match statement, but like, you know, it's also kind of like pattern matching kind of thing. Yeah, pattern expression. That's why you can do this, because this is the pattern. This is matching this. So x1, y2, z3. But if we do this, then we'll have the crap that the compiler is not happy because this doesn't match. Yeah, so that's how the last statement work. We could ignore one, so using underscore dot dot dot. So if you just want to ignore one, you can comma and an underscore here. If there's multiple, you just want to ignore, you can use dot dot dot. I think that we have seen that before. Ignore vary in a pattern. Functional parameters. So full. This is X part is a pattern, because when we use full, then that is also expression. Yeah, just like let. So for example, X and Y, of course the reference of X and Y is a pattern, and then we call it here. So this one will match. Oh no, actually it's a reference to a tuple with two X and Y, which is both I32 here. So yeah, this one will match because it's a tuple. Point is a tuple with two integers. Yeah, so it's everywhere. The pattern expression thing is everywhere. We have seen all of them before. We're just not aware that they are who they are. So that's what it is. So next, refutability. What's that? Or did I read it wrong? What is refutability? Whether a pattern might fail to match. Patterns are refutable or irrefutable. Patterns will match for any possible values. Past are irrefutable. So x5, x matches everything, cannot fail to match. Pattern that can fail to match for some possible values are refutable. For example, some x in the expression, if a variable is none rather than some, then it will not match. So x will match anything, because like we don't even specify the type, right? It will be inferred by the 5 here, so it's I32. So this is irrefutable, but refutable ones are more complex. The pattern can fail to match. Less statement and for loop only accept irrefutable patterns. So if the less statement and for loop doesn't match, then it will not compile, because it can't do anything meaningful. But then if let and while let can have refutable and irrefutable pattern, because compiler will warn against irrefutable pattern, because they are supposed to handle possible failure. Because if let, right, you will have times that it doesn't match, then it will just go to the else or discarded. And while let, if it failed to match, it will stop. So if it always match, then you have an infinite loop. So that's why you get the compiler warning. Same as if let. If you're doing that, why are you using if let? Why are you not using let? So in general, you shouldn't have to worry about the distinction between refutable and irrefutable pattern. However, you do need to be familiar with the concept of refutability, so you can respond when you see an error message. You need to change either the pattern or the construct you're using. So, for example, here let some x equals to some optional value. The some optional value was a non-value, failed to match, meaning the pattern is refutable. However, the let statement can only accept any refutable pattern. So if I use if let now, then it will be fine, right? Yes, and then I can print it out as well. We didn't cover, only cover every value. Compiler error. Yeah. So for example, we do if left 5 here, we have a warning here that's saying, yeah. So yeah, so that's why I suggest using let, because if it always match, then why are you using if let? Just let x equals to 5 and then print x. So that's what happened. Yeah, so basically that's it for the next one. Well, we are quite quick in this chapter. Maybe we can read Unsafe Rust today. That would be fun. And tomorrow we can do the project, and then when we come back we can do rustling. Actually, that would be great. Let's see if I will fall asleep reading Unsafe Rust. I think I'll be too excited to go to sleep. If we, I love dangerous things. Unsafe Rust is cool. Okay, so chapter 6, mesh patterns. Sample, we can do this, match, and then anything else. It's very straightforward. Yeah, so it's matching literals, matching name variables. We have sum here. So we can also have sum 50, sum y, so so again, like this is the thing that's quite dangerous if you do something more complicated. I think we see some tricky thing here before, but this one is quite straightforward. So 5 doesn't match this one, so it'll match y, and then we'll just print a y here. Any other thing, for example none, then we'll have something else. But here this y is not this y because this is inside here. It's in a different scope, right? So new y bound to the inner value. So yeah, at the end it will be still be 10 because this y is different from this y. Is in this scope. Yeah. Meshed y equals to 5. Then yeah. So in that case, it will print out, yeah. Default value. So it will become, yeah, it will be none. Yeah, to create a match expression that compare the value of the outer x and y rather than introducing a shadow variable, use a mesh guard condition. Remember that? Remember that? I don't remember. Let's have a look. Mesh guard. Yes, if x percent 2, so we can have like if x equals to that y, which is that 10y. So we can say like that. And if n equals to, so this one will refer back to this y instead of a different scope of y, so we can use it like that. We use if. It's like a guard, conditional guard, something called extra condition with mesh guard. Multiple patterns, we've seen this before. 1 or 2, they will mesh this one. We can also 1 to 5 mesh this 1 through 5. So it's not just limited to numbers, it can also use characters, just like between these two code points. So it's like A to J, early ASCII character. This is so cliche. I've seen this like in other programming language example as well. They structure the break apart values. So for example, we have point struct, so x and y are both integers, so we can also match. So a and b here to match the point. So, actually this is just let, so we have those. We've seen this before. We have also, what's the difference between these two? What's going on? A and B. Oh, x and y. So yeah, this is a shorthand. You don't have to type the x colon A and B. So this one is creating A and B already. So if we use it on a match P, so it got x and y needs to be 0. This one x equals 0, if not then it's on here. The destructuring enums, or again with enum, we have seen this before again. It's just reminding us what we have seen before with xy. So xy will be this 2xy here. Change color, so it will be RGB here. So we'll go here. nested structure and enums, more complicated stuff. So now change color with color, HPG or HSV. And then if I want to match, so match change color, inside we have RGB or inside we have HPG. You can also do that as well. It's nested, but it's fine. Destructuring structures and tuples. So what's going on here? We have a tuple of numbers, feet, the inches, and then point. So this again is like a nested thing. It will still work as long as it matches. It will work. Ignoring values in a pattern. I'm starting to get more and more tired. That's why I'm like speaking softly. I'm going to bed. Okay. Ignoring values in a pattern. So yeah, this is what we do. We don't care about the first one. So we use underscore. Yeah. Ignoring part of the pattern, as long as it's something and something, that's fine. Otherwise, it would just go here. Yeah, setting values equals new values. Can override existing values. Again, we have seen this. We only care about the 1/3 and 5th. So we can use underscore. So this one, because it's unused, right? We have done this many times, but we don't get a warning about using X because it's unused. So we add the underscore in front of the variable name, so it won't get the warning about unused variables. So for example, we do this. We don't really care about this S here. So we just have a underscore S here. Doesn't bind at all. Yeah, so the difference between using just underscore and then underscore X is that because underscore X you still have the value, but underscore just doesn't. So we received an error because so here S so equals some string. If let's S is something, then we have this. So yeah, so because this, the string inside, has been extract and match and bind to underscore S, right? So the ownership has shifted, so now we can't see S anymore. But if we do this, it won't get extracted, so it will still be fine. So this one is fine. This one is not. We got the crap. Yeah. Ignoring remaining part of a value. ... So we don't only care about the first one. We can use ... to ignore the rest of it. Yeah, you can first and last, and the rest we don't care. This will have a problem because I don't know where is second. Because ignoring 2 at the beginning, ignoring 3 at the beginning, and ignoring 1 at the beginning. The second, well, we can read second, but the machine don't know what is second, right? So yeah, I don't know which one is this. So you can only use ... in a list or a sequence, which only once. Yeah, can only be used once for tuple pattern. Extra conditions. So yeah, we are talking about the mesh guards again. That so this for this one, X need to be divided by 2 to mesh this. Otherwise, it will mesh this one. So this one then we can compare with y, because if we say y here, then this y will be another y. It will match whatever, it will be 5, right? So it won't work. So or we've seen this before as well, I think. Add binding. Oh yeah, this thing is actually, if we write like this, is actually this 4. So if y, so x is 4 or 5 or 6, and then if y, if condition applies to the whole pattern, rather than this, so this will also be, well, so it's false, right? So 4, 5 or 6, and if y is true. The reason is that if condition applies to the whole pattern, yeah, so this one actually will go to the second branch, because this is true but this is false, so it won't work. But if you think, oh, it's only this, then 4 should match, then it should be here, but it's not. But if you put a bracket here, it will be the first arm, so it will be yes. Add binding. Message hello. So id equals to 5. Id variable add. So we'll bind this to here, but at the same time we're checking whether it's between 3 and 7. So find id range 5. Test the value and save it in a variable within one pattern. Yeah. Yeah. I wonder, can I do it like that? Add. So match that n and then add n equals to y. Does it need to be a range? Okay. Yeah, I wonder whether you can do that as well. REST pattern very useful in distinguishing between different kind of data. Right. So we're done for chapter 13, chapter 19. Should I quickly? Yeah, let's just quickly read through this. I think this is the territory that we would have to come back eventually anyway. So because this is more advanced things, I don't think we'll use that anytime in the near future. So before we do one more project, we look at a few aspects of the language you may run into every once in a while, but you may not use every day. So we may forget about it and come back, but it's good to have a glimpse about what we may run into someday. Use this chapter as a reference for when you encounter any unknowns. Are useful in very specific situations. You may not reach them often. Yeah, so we'll just quickly read through it. In the future, come back to here when we need to. And save Rust. Woo! Advanced traits. Should I say types? Yeah, I think we've seen a little bit of unsafe before. Advanced types, so advanced functions, so everything is advanced. Enclosures, macros. If you want to write your own macro, you can. Normally you don't. Unsafe Rust, we've seen a little bit of that. So if we are doing the thing that follow the Rust memory safety guarantee, then it's safe Rust. If you do something that is not, then it's unsafe Rust. Second, language hidden inside it doesn't enforce this memory safeguard guarantee. Unsafe Rust, just like regular Rust, give us extra superpowers. Unsafe Rust exists because, by nature, static analysis is conservative. When a compiler tries to determine whether or not code uphold the guarantee, it's better for it to reject some valid programs than to accept some invalid programs. Although the code may be okay, if the Rust compiler doesn't have enough information to be confident, it will reject the code. In these cases, you can use unsafe code to tell the compiler, trust me, I know what I'm doing, so don't worry. But be warned, however, that you use unsafe Rust at your own risk. If you use unsafe Rust code incorrectly, problem can occur due to memory unsafety, such as null pointer dereferencing. Another reason Rust has an unsafe alter ego is that the underlying compiler hardware is inherently unsafe. If Rust doesn't let you do unsafe operation, you wouldn't do certain tasks. Rust needs to allow you to do low-level system programming, such as directly interacting with the operating system or even writing your own operating system. Working with low-level system programming is one of the goals of the language. So, so superpower of unsafe Rust. Switch to unsafe Rust, use the unsafe keyword and then start a new block that hold the unsafe code. You can take 5 actions in unsafe Rust that you can't in safe Rust, which we can call unsafe superpowers. This superpower includes the ability to dereference a raw pointer, so now it's like C, call an unsafe function or method, access or modify a mutable static variable. Ooh. Implement an unsafe trait, access field of union S. What does it mean? Important to understand that unsafe doesn't turn off the borrow checker or disable any other of the Rust safety check. If you use a reference in unsafe code, it will still be checked. The unsafe code only gives you access to these 5 features that are then not checked by the compiler. For memory safety, you will still get some degree of safety inside of unsafe block. In addition, unsafe does not mean the code inside the block is necessarily dangerous, or it would definitely have memory safety problems. The intent is that, as the programmer, you ensure the code inside unsafe block will access memory in a valid way. People are fallible and mistakes will happen, but by requiring these 5 unsafe operations to be inside blocks annotated with unsafe, you'll know any error related to memory safety must be within the unsafe block. Keep unsafe blocks small, you'll be thankful later when you investigate memory bugs. To isolate unsafe code as much as possible, it's best to enclose unsafe code within the safe abstractions and provide a safe API, which we'll discuss later in this chapter when we examine the unsafe function and method. Part of the standard libraries are implemented a safe abstract over unsafe code that has been audited. Wrapping unsafe code in a safe abstractions prevent use of unsafe from leaking out into all places that you or your user may want to use functionality implemented with unsafe code, because using a safe abstraction is safe. Let's look at each of the 5 unsafe superpower. We also look at some abstractions that provide safe interface. Dereferencing a raw pointer. Woo! Dangling reference section mentioned that a compiler ensures the reference are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to reference. As with reference, raw pointers can be immutable or mutable and are written as star const t and star mut t respectively. The star isn't the dereference operator, is part of the type name. in the context of the raw pointers, immutable means that the pointer can't be directly assigned to after being dereferenced. Yeah, it's starting to get to be like C. Difference from reference and smart pointers, raw pointers are allowed to ignore the boring rules by giving both immutable and mutable pointers or multiple mutable pointers to the same location. So yeah, now we can point whatever we want. We don't have that like only one mutable pointer rule. Aren't guaranteed to point to valid memory. Are allowed to be null. Don't implement any automatic cleanups. So just like pointers in C or something like that. By opting out of having Rust enforce this guarantee, you can give up guaranteed safety in exchange for greater performance or the ability to interface with another language or hardware where Rust guarantee don't apply. So now we have number 5, and then reference 1 is the reference of num as a raw pointer that is immutable, or we have a mutable reference of num to a mutable reference. Note that we don't include unsafe keyword in this code. We can create new raw pointer in safe code. We just can't dereference raw pointer outside of unsafe block, as you'll see later. We have created raw pointer by using us to cast an immutable and a mutable reference into the corresponding raw pointer types. Because we created them directly from reference, guaranteed to be valid. We know these particular raw pointers are valid, but we can't make that assumption about just any raw pointers. Yeah, because we're just referencing them, right? So this is still valid, this is still valid, but then after that, then it's not. Demonstrate that. Next, we'll create a raw pointer whose validity we can't be so certain of. It's just have an address, and address is a pointer. So this one we don't know. Arbitrary memory is undefined. Maybe data at the address or maybe not. The compiler may optimize the code so there's no memory access, or the program may error with a segmentation fault. No good reason to write code like this, but this is possible. So this is totally unwise to do it like that, but you can do it like that if you want, if you really want. Recall that we can create raw pointers in safe code, but we can't dereference raw pointers and read the data being pointed to. So this is fine, and after that, if we want to dereference it, we have to put them in a safe block. Creating a pointer, there's no harm. It's only when we try to access the value that's dangerous. So yeah, so try to create a both. So yeah, we have both a mutable and immutable pointer, right? So that points to the same memory location where num is stored. The code would not have compiled because Rust ownership rule doesn't allow. Using raw pointers, we can do that. Yeah, but this is dangerous. Over this danger, why would you ever use raw pointers? One major use case is when interfacing with C code. Exactly, because C works exactly like this. See the next session, currently unsafe function or method. Other cases when building up on safe abstractions that borrow checkers doesn't understand. Yeah, we'll explain later. calling an unsafe function or method. So second power. Second type of operation you can perform in an unsafe block is calling an unsafe function. Look exactly like regular function and methods, but they have an extra unsafe before the rest of the definition. So instead of func dangerous, you have unsafe func dangerous. The unsafe keyword in this context indicate the function has requirements we need to uphold. Rust now don't guarantee that it meets the requirement. So yeah, when you use dangerous, you have to put it in an unsafe block as well. Just call the dangerous function within unsafe. Yeah, this is what you have to do. Yeah, without the unsafe block, you will get the error. So how to create safe abstractions over unsafe code. So here we have this. So split at mu3. So V is so R is mutable reference. You want to split the two, right? We can implement this function using only safe Rust because you have two mutable reference, right? An attempt may look something like this. So you have a mutable reference and create two mutable reference. As a function rather than a method, only for slice. Generate type T, yeah. This one compile because the function first gets the total length of the slice. Then it assert the index given. So these two are actually pointing at the same place, right? So two mutable reference. We pass an index that's greater than the length. Panic before it attempts to use that index. Yeah. So this is to check, right? Like if the splitting point is outside of the length, of course it will panic, so it will crash. Then we return to a mutable reference. The start of the original slice and the mid. Yeah. Raw checker can understand that we are borrowing different part of the slice. It only knows that we are borrowing from the same slice twice. Borrowing reference. Oh, so the problem actually is these two, pointing to the same back, but actually we're pointing to here, but it doesn't know. From the same slice twice. Different part of a slice is fundamentally okay because two slices aren't overlapping, but Rust isn't smart enough to know this. We know that the code is okay, but Rust doesn't. It's time to reach for unsafe code. So first we would have to create an unsafe block within the function. So we have to create the raw pointer as well. The slice type section in for slice I pointed to some data and the length of the slice. Use the length method to get the length of the slice and a smooth part method to access the raw pointer of a slice. Because we have a mutable slice, a smooth part returns a raw pointer. This one is not implemented yet, right? Just call it somewhere. From raw part mu. So, but anyway, this is supposed to be a raw pointer within the type. So in part. we keep the assertion that, yeah. Then we get to the unsafe code. So this is fine. We're creating the pointer. We're not referencing it. But if we're doing that from raw parch mute, then this one we're using it. This one we're using it. Yeah. Add meet. So it go from the top to there, and then yeah. This is unsafe because we're using this pointer here. This is unsafe because it takes a raw pointer and must trust this pointer is valid. Add method is also unsafe. So many unsafe functions. Yeah, but because this is like just messing around with the raw pointer, so probably very unsafe. We don't need to mark this as unsafe because the unsafe code is contained. Yeah, because we can tell this function from safe, call this function from safe Rust. We've created a safe abstractions to unsafe code. Yeah, so everything in the unsafe block is okay. This thing is safe because the unsafe is contained. Everything is good. We have created safe abstractions to unsafe code with implementation of the function that uses unsafe code in a safe way. Create only valid pointers. So now everything's good. In contrast, the use of slice will likely crash when the slice is used. This code takes an arbitrary memory location and create a slice. Oh. Yeah, it just go from the address. Yeah, this is totally random, so this is not safe. This will crash. This is irresponsible. Someone do this. Someone do this. And accessing something. We won't. We don't own the memory of that. Yeah. This is not good. Don't do this. This is okay. This is not okay. Using extern function to call external code. So now we're using Rust with C. Sometimes your Rust code may need to interact with code written in another language. For this, Rust has the keyword extern that facilitates the creation and use of foreign function interface, FFI. FFI is a way for a programming language to define functions and enable different foreign programming language to call those functions. We have apps function from C standard libraries, extern. Blocks always unsafe to call from Rust code. Other languages don't enforce Rust rule and guarantee. Rust can check them. So we are using extern C and then calling this function. And then if we call, if we use apps, this apps here, then it's unsafe. Within the extern C block, we list the name and signature of external function from another language we want to call. The C part define which application binary interface, ABI. The external function uses the ABI defines how to call the functions. At the assembly level, the C ABI is the most common and follows C programming language ABI. We can also use external create an interface that allow other language to call Rust functions. Is that what Pile3 is doing? Instead of creating a whole extern block, we will add the extern keyword and specify the API to use just before the fun keyword for the relevant functions. we also need to add a no mangle annotation to tell the Rust compiler not to mangle the name of this function. Mangling is when a compiler changes the name we have given a function to a different name that contains more information for other parts of the compilation process to consume is less human readable. Every programming language compiler mangles names slightly differently. So, for Rust function to be nameable by other languages, we must disable the Rust compiler's naming mangling. So don't mangle the name, and so this is called from C function. So pub extern C func, just call a Rust function from C here. This usage of extern does not require unsafe because everything's supposed to be written in Rust and is called by C. If C is unsafe, it's C's problem. It's not our problem in Rust. So don't need to do that. Accessing or modifying a mutable static variables. So this book, we have not yet talked about global variables. Rust does support, but can be problematic with Rust ownership rules. If two threads are accessing the same mutable global variable, it can cause a data race. So in Rust, global variables are called static variables. So, for example, a string slice. So hello world is actually static. Hello world is actually this string slice. Similar to constants, variables and constants, the difference. Name of static variables are in screaming snake case, so all cap and snake case. Static variables can only store reference within the static lifetime, which means the Rust compiler can figure out the lifetime and we aren't required to annotate it explicitly. Accessing an immutable static variable is safe. A subtle difference between constant and immutable static variable is that the value in the static variable have a fixed address in memory. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate the data whenever they are used. Another difference is that static variables can be mutable. Accessing and modifying mutable static variable is unsafe. So actually static variable can be mutable, which is that they are stored in a fixed place, but technically they can be changed, but they are unsafe if you do that. So static mu, static mu counter, add to count, unsafe because you're changing it. You have the reference because it's global, the name is global, right? To count, bring reference, unsafe. Regular variable we can specify. Using mu keyword, any code that reads or writes from count must be written within unsafe block. This code compiled and print would likely result in a data races. With mutable data that's globally accessible, it's difficult to ensure there's no data races, which is why Rust considers mutable static variable to be unsafe. Where possible, it's preferable. I'm sorry, I'm getting tired. Where possible, it's preferable to use the concurrency technique and thread-safe smart pointers that we have talked about before in chapter 16. So the compiler checks that the data accessed from the different threads is done safely. I think I'll finish this part of the chapter and continue the rest of the chapter tomorrow because I don't want you to fall asleep. I'm falling asleep. Everybody's falling asleep. That's not good. Okay, so implementing using unsafe traits. We can use unsafe to implement unsafe traits. A trait is unsafe when at least one of these methods has some invariance that compiler can't verify. We declared a trait is unsafe by adding the unsafe keyword. So implementation of the traits are unsafe too. So unsafe traits, so any implementation are unsafe. You say unsafe impel, we are promising that we will uphold the invariance that the compiler can't verify. So again, responsibility is on your shoulder. As an example, we record sync and send marker trait that we discussed. The compiler implements these traits automatically if our type are composed entirely of send and sync types. If we implement a type that contains a type that is not send or sync, such as raw pointers, then we want to mark that type as sync or send. Then we must use unsafe. Yeah, remember that, right? We talk about yeah. Rust can verify our type upholds the guarantee. So accessing fields of a union. Union is similar to struct, but only one declare field is used in a particular instance at a time. Unions are primarily used to interface with unions in C code. Okay. Accessing union field is unsafe because Rust can't guarantee this type of data currently being stored in union instance. So we're gonna not dive more. It just means that union is designed to use with C because C is again not like Rust, so it's unsafe. So that's why it's unsafe. When to use unsafe code? Using unsafe to take one of the 5 actions just discussed isn't wrong or even frowned upon, but it's trickier to get unsafe code correct because the compiler is not helping you. Now, when you have a reason to use unsafe code, you can do so. But you have to explicitly say that, and it's easy to debug when anything goes wrong. Yeah, I can't remember this send and sync thing. I may have a read when I'm off screen, but yeah, let's continue tomorrow. I'm super tired. You are super tired. I don't want to dragging on for so long. So let's continue tomorrow for the rest of chapter 19 for these advanced things and macro, and then we'll do the final. Well, we'll see if we have time for the final project. We'll see. I'm quite busy. Yeah, I'm always busy. I'm sorry about that. But anyway, I'll see you tomorrow, one way or another. So see you. Bye.